Okay, so welcome back. Well, in this video, I wanted to make an explanation of my thesis work that I have made for my PhD. My name is Eric Axel Martinez Rios, and the title of this presentation is Analysis of Wavelet Transforms for Signal Classification. Okay. Well, the presentation is structured as follows. First, I will make a brief introduction about the topic. Then I will talk about the hypothesis and objectives. And well, this thesis or this thesis work is divided into analyzing two main case studies. First, we analyze the problem of how can we detect pavement transverse cracking detection using acceleration data. And we draw some conclusions from that case study. And also, we analyze the problem of water leakage classification. No? That is the second study that we analyze in this work. Okay, well, when we talk about the analysis of signals, we can divide this analysis into three general frameworks. First, we have the time domain analysis that is interested in how the amplitude of the signal changes with time. Also, we have the a frequency domain analysis that is concerned with the spectral content of the signal obtained via the Fourier transform. And finally, we have the time frequency analysis that is characterized by understanding what is the spectral content of the signal that changes over time. No, we want to study how the spectral content of the waveform changes with time. Okay, that is the main goal of time frequency analysis and is the main focus of this presentation. And well, why we are interested in studying these signal representations in the context of classification? Well, typically, we are interested in studying these type of representations because based on these representations, we can compute features or statistics that can help us to compute descriptors that can help us to classify the signal that we want based on different, for any kind of classification problems, okay? In the time domain analysis, typically you can compute the statistics. In the frequency domain analysis, you compute statistics based on the frequency spectrum. And in the time frequency analysis, you can compute a short time Fourier transform or a wavelet transform. There are the two main techniques that we can use in order to generate a time frequency representation of any signal in order to extract these features. And well, if we discuss a little bit about um, these time frequency analysis techniques, well, we have, for example, the short time and the short time Fourier transform and the wavelet transform. In the case of the short time Fourier transform, what we are doing, well, before that, well, I want to explain this first. As I mentioned before, in the time domain analysis, you are analyzing how the amplitude of the waveform changes with time. In the frequency domain analysis, you are interested in the frequencies that that compose your signal. No, you want to compute the amplitudes of the frequencies that are contained in the waveform that you are studying. But in the short time Fourier transform, what you are doing is to say, okay, I have my signal and I will divide my signal into different signal segments or signal windows. And I will apply the Fourier transform to each of these windows, okay? And by doing this, we generate a 2D mapping that we call the spectrogram. And by computing this spectrogram, we can understand how the frequencies of the signal evolve over time, okay? What is the main problem of using or computing this spectrogram? Well, the problem is that the resolution that we can obtain in this time frequency plane is limited. For example, if we use a very short window size, you can have a better time resolution, but you decrease the frequency resolution. On the other hand, when you increase the time resolution, the size of the window in the time domain, you will get a worse time resolution, but a better frequency resolution. And this trade-off between time and frequency is known as the Heisenberg uncertainty principle, that basically states that it is not possible to arbitrarily concentrate a function in time and frequency simultaneously. And one of the techniques that can help us to overcome to a certain extent this Heisenberg uncertainty principle, or to overcome the time and frequency resolution that we can get from the short time Fourier transform of the spectrogram, is to use the wavelet transform. And when we are using this wavelet transform to generate this time frequency mapping, we are essentially computing what we call a multi-resolution analysis. And the idea is that, well, instead of having a fixed window size over time, what we can do is to change the size of the window as we decrease in frequency. In this case, the lower frequencies will have a better, as a worse time resolution, but as we increase in frequency, we can decrease the size of this window. And in order to change the size of this window, as you can see in this figure, we need to use a basis function that we call the wavelet, no? So the wavelet is essentially a function that we can stretch in time or compress in time as we move in frequency, no? For the higher frequencies, we will have a better time resolution, but as we decrease in frequency, we will be increasing the size of this window, or the expansion of this window, or this function, okay? And this function is essentially what we call a mother wavelet, okay? And well, typically we want to use this time frequency representation to compute features. No, that is the main concern about this. No, we want to compute useful statistics that can help us to classify the signal. No, so we have machine learning techniques that typically require this feature extraction process. For example, think about a decision tree, a candidate's neighbor, a supervector machine, the the logistic regression, any type of regression trees requires this feature extraction process from a signal in order to train those models. But the problem in the particular case of time frequency representations is that computing this feature is challenging because there is no precise method for selecting the appropriate basis function, okay? And this is related to the fact that we have many types of wavelets, okay? In the literature, you can select many families, no? Many type of functions that can help you to perform this signal decomposition. But the problem is that, well, how can we select this, no? And this challenge of using time frequency representation, because the problem is that the parametrizations of the short time and the wavelet transform is quite complicated because there are no guidelines that tell you about how you should parametrize the decomposition that you want to make. And this is related to the Heisenberg uncertainty principle that we discussed previously, and also the diverse set of wavelets, no, that we have. We have the Gaussian, Verlet, Morlet, Shannon, etc. But the problem is that, well, how can we know which is the best one? How can we compute these features in an appropriate manner? And well, this led us to the research question, no? That is, what are the properties of a model wavelet that should be considered to generate a time frequency representation for signal classification? And this is relevant because typically we want to use these time frequency representations to perform signal classification. But the problem is that when we are computing this wavelet transform, we are essentially computing a dot product. In other words, we are computing a correlation between the function that we want to analyze and the model wavelet for every frequency and for every time. Okay, so we are expecting that the function that we are using to perform this decomposition has some degree of similarity with the function that we want to analyze in this time frequency plane. So the hypothesis, it is conjecture that the generalized Morse wavelets could provide a basis to select an appropriate model wavelet that helps to generate a time frequency representation that can be used for classification. Here I am presenting the general form of these generalized Morse wavelets. Some aspects that I want to highlight from these type of functions is that they are analytical. That means that they are only supported for the positive frequency spectrum. That is important because based on analytical wavelets, we can characterize the transients of the waveforms. Also, well, we need to pay attention to two parameters that appear in this function, that is beta and gamma. So the idea of these parameters is that you can change the values of those parameters and you can get many types of wavelets. Okay, you can get the Shannon, the Airy, the derivative of Gaussian wavelets by only changing these parameters. So the idea of the reason that they are called the generalized Morse wavelets is that you can get many wavelet functions by only changing these values. Okay, so this is one of the techniques, no, that we want to use for this work. But also we wanted to make a comparison with another way to compute these features. Typically, when we are using this wavelet transform, well, we need to select the wavelet, and based on that, we can perform or generate these spectrograms or these scatograms that represent the time frequency information of the signal. But there is other technique that is also based on wavelets that is called the wavelet scattering transform. And the scattering transform basically is a signal decomposition technique, no, that can help you to extract useful features for classification by generating a representation that is translation invariant and also stable to small time wrapping deformations or small scalings in time uh, or in frequency, no? So the idea of this thesis work is that we will be comparing these two approaches of using the wavelet transform to perform signal classification. No, we want to view what is happening to the results that we get from a classification problem by using these two approaches. Okay, and also understanding how we can select these wavelets. Okay, so this is like a secondary technique that at least for the second case study, we use it as a means of comparison. And also in the second case study, this technique will take the central point because this technique was was less frequently used in the literature compared to the classical approach of using the wavelet transform. So I will be discussing a little bit about the differences between these two techniques along this study and the comparisons that we make by performing these or testing these two approaches. Okay, so the first one is we want to employ the wavelet transform through the generalized Morse wavelets to generate a time frequency representation that can be used for signal classification. And the second objective is that we want to employ the wavelet scattering transform as a feature extraction technique for signal classification. And well, we will be analyzing two main case studies. We have the first one is how we can detect pavement transverse cracking based on the vehicle vertical acceleration. And the second problem is how can we detect water leakages based on vibration, pressure, and hydrophone data. So talking a little bit about the first case study of pavement transverse cracking detection, I want to make a brief overview of the motivation, no? Why we want in the first place to detect these cracks in the asphalt pavement. No? Okay, so well, the motivation. Um, well, the first thing to take into account is that well, these payments or this deterioration in the payment is related to the payment age, the weather conditions, the traffic logs, and the lack of maintenance. This degradation of the road surface can produce cracks, potholes, speed bumps, and grooves. And these deviations present in the road surface can cause potential harm to vehicles, vehicle users, and pedestrians. And well, the typical way in which this condition of the road is evaluated is by using pavement condition index surveys. The problem is that making this service is time consuming and also prone to errors, no? And also they are not too safe for the technicians of the road when they are making their inspections. So this motivates or has motivated the use of different approaches for detecting these road surface anomalies. There are different ways in which this can be performed. For this work, we focus or we constrain the analysis to analyzing how can we make this by analyzing the vibration of the vehicle. So we call these vibration-based techniques for road surface anomaly detection. And well, in general, we can classify the approaches by using thresholds. Basically, they are measuring the vibration signal and they are setting a threshold, no, to detect the anomaly in the road surface. Also, we can use feature extraction plus machine learning techniques. But the constraints about these two approaches is that, well, for the case of thresholds, you need calibration. For the feature extraction, well, the challenge is how can you compute those features? No, there are many ways in which you can extract those statistics, but there is no standardized features that can help you to detect the surface anomalies, which makes the feature extraction challenging. And also you can use deep learning. The problem of deep learning is that you need high computational power and large sample sizes. So there is another constraint that we have, no, when using these approaches. And here in table one, what I'm showing you is like an overview of some of the works that have used vibration-based techniques for road surface anomaly. As I mentioned before, you can compute thresholds, you can use time and frequency domain features. Based on those features, you can train different machine learning classifiers like the Gaussian mixture model, the decision tree, convolutional neural networks, and so on. And as you can see, these performance or the techniques that have been used have obtained a relatively high performance. Okay? Okay. So, well, as I was mentioning, all of these, all of this literature tells about that many of the features that we can use for feature extraction um, have already been used in the literature, and that the accuracy that they can obtain is relatively high. No, and but well, also well, if we analyze in concrete, the literature that have used time frequency representation, we can use that there is a lot of heterogeneity related to the type of time frequency method that have been used. For example, the short and Fourier transform, the continuous wavelet transform, the discrete wavelet transform have already been used. And also the parameters are typically set arbitrarily, no? Because, well, you need to define the window type, the length of the window, and the overlap between windows when you are computing a short time Fourier transform, or when you're using the Debauches wavelets, no? Or, well, why we are using the Debauches wavelets, we have different orders of these wavelet types. How should we select them? Okay? So there is a lot of studies that use these methods, but there is no consensus or guideline that tells you how you should conclude that this is the best for your case, not for your application. And well, typically these parameters of these methods are set arbitrarily or via trial and error, no? So, well, here I wanted to outline some of the gaps that we have identified in the literature that is concerned with pavement transverse cracking detection. As I mentioned before, we have the trial and error selection of the parameters of time frequency methods. Also, that there is no discussion related to what are the underlying properties of the model wavelet that you need to take into account to select it. And also in some works, the model wavelet that they use to perform the wavelet decomposition is not reported. Also, transfer learning, no, that is this idea of taking a pre-trained model with predefined weights and adjusting them based on the new data has not been explored. Also, the majority of the works have been focused on detecting potholes and speed bumps. And also, as I mentioned before, well, there are heterogeneous results among the studies because, well, every author used different data sets, every author used um, where analyze different anomalies. So it's really complicated to know which is the best one for our case. Okay. So, well, the idea is that we want to perform this pavement transfer detection and also try to fill some of the gaps that we have discussed in the previous slide. So to this end, we'll be analyzing a dataset, a publicly available dataset that consists of vehicle vertical accelerations data associated with the presence and the absence of pavement transverse cracking. Also, well, we take the continuous wavelet transform of this acceleration data of the vehicle, but contrary to the literature, we will be using the continuous wavelet transform and the generalized Morse wavelets, but we will be selecting the parameters of these tools by using two metrics, the Heisenberg area and the reconstruction error. And based on these metrics, we will be computing the scalegram of these signals to fine-tune three pre-trained convolutional neural networks that are the GoogleNet, the SqueezeNet, and the ResNet 18. The reason of using this approach is, well, hasn't been exploring the literature, at least from the time that we make this study. And also, one of the disadvantages of using deep learning, for example, is that you need large sample sizes. So transfer learning is the approach that can help us to overcome this problem of having a limited sample size. So also, we wanted to make a comparison of the methods that we have used with the related research. So to this end, we have used a publicly available dataset that was reported in the work of Yang and Xu that is called Application of Signal Processing and Support Vector Machine to Transverse Cracking Detection in Asphalt Pavement. The dataset was collected in Shanghai, China. It consists of vehicles' vertical acceleration data associated with pavement transverse cracking. Also, well, they use a piezoelectric accelerometer. The sample frequency was 1280 Hz, and the sensor was placed in the front tire suspension knuckle of the vehicle. And well, this dataset was recorded at different velocities, 30, 40, and 50 kilometers per hour. And also the cracks that we wanted to identify have a width between 2 to 13 millimeters. And also the sample size was relatively small of 327 signal segments. So that is one of the main reasons that we wanted to study this dataset because it was relatively small, so we can take advantage or test this approach of using transfer learning. Also, there are some results that were already published by using this dataset. So that is why we decided to use this dataset for comparison of our method. Also, here in figure 4a, you can see the illustration of the transverse cracking that they were identifying. This is the transverse cracking, and this is the crack section. Also, you can see in figure 4 the distribution of the dataset. Here you can see that 32% of the dataset were associated with transverse cracking, and 67% was associated with a crack pavement. So that is another consideration to take into account. Okay. So, well, as I mentioned before, in order to compute these scalar variance based on the data set that we have, we use two metrics. We use first the Heisenberg area. What is the Heisenberg area? It's basically a metric that tells you about the degree of energy concentration of a function in the time and frequency domain simultaneously. You can compute this Heisenberg area by using this expression that is basically computing the multiplication between the standard deviation in the time domain times the standard deviation in the frequency domain. So we compute these two standard deviations, and we can compute the Heisenberg area. And for the generalized Morse wavelets, here you can see what are the changes in the Heisenberg area for different values of gamma and beta. Remember that, well, in the previous slides, I mentioned that um, you can change the form or the form of the wavelet or by changing these two parameters, beta and gamma. And for the particular case of generalized Morse wavelets, when you set gamma equals to 3, you can approximate the lower bound of the Heisenberg area, that is 1 over 2. That means that this is the lowest degree of uncertainty that you can get from this type of functions in the time and frequency domain simultaneously. And this Heisenberg area lower bound is also a result of the Heisenberg uncertainty principle. So we can say, or we can set the value of gamma equal to 3, because in this region is where we approximate this Heisenberg area lower bound. The problem that we have is that you can observe in this region that um, that there is infinite values of beta that, well, you need to set. No, in this region, no, there is a lot of values that beta can take between 60 to 0. No? So the question that remains is, how should we set the value of beta? By setting the value of gamma equal to 3 according to the Heisenberg area lower bound. Now, how should we get the correct value that we need? So to do that, we will be, well, before that, I wanted to make an extension of this explanation. Here in figure 6a, you can see the behavior of the Heisenberg area when we set gamma equals to 3 and we are increasing the value of beta. You can see that the Heisenberg area is very close to 0.5, that is 1 over 2. Here you can see that we have 0.53, and you can see how as we increase the value of beta, we are getting closer to this Heisenberg area lower bound. And on the other hand, you can see the decomposition of this Heisenberg area in the standard deviation in the time and frequency domain. And you can see that as you increase the value of beta, you're increasing the dispersion over the standard deviation of the function in the time domain. Okay, so you're increasing that uncertainty in the time domain, and you are slightly changing the uncertainty in the frequency domain. So there is an effect, no, of these parameters when you want to use the generalized Morse wavelets, no, because there is no rule into how you should do that. No? Okay. So in order to set the value of beta, we propose the following methodology. The idea was, okay, we have the signal, and we can compute the wavelet transform by setting gamma equals to 3. Beta, we can set it arbitrarily, and also we are also uh, changing the value of the voices per octave. We can obtain wavelet coefficients that are basically the results of the correlation between the wavelet and the signal that we want to study. We can compute inverse wavelet transform because we can compute, well, the wavelet transform is invertible, so we can reconstruct the signal, and we are expecting that the reconstruction of this signal is as close as 0 as possible. That is, that we are wanting to measure the difference between the original signal and the reconstructed version obtained from the wavelet transform coefficients. So if we set the parameters correctly or adequately, maybe we can get a mean square error that is close to 0. Okay, so this is only the square error of only one signal, but we have a data set of signals. So we want to compute the average of all the square errors of all of the signal segments that we have in the dataset. And we propose to use the average of all of these errors. We call this the average reconstruction mean square error that can be computed in this way. And well, this is the surface that we obtain from the average reconstruction mean square error by changing the value of beta between 1 and 20 and the value of voices per octave between 1 and 10. And based on this analysis, we saw that the minimum average reconstruction mean square error occurred at the position of beta equal to 1.33 and also 1 voice per octave. So we use these parameters to compute the scalograms that we'll be using to fine-tune the pre-trained convolutional neural networks. This is the position or the parameters that we will be using to perform these scalograms. So the idea is, okay, we know now the parameters, we can compute or generate a scalogram, and based on this scalogram, we can fine-tune these pre-trained convolutional neural networks, okay? So in this case, since we want to take advantage of this transfer learning approach, we decided to test the pre-trained neural networks that are available in the literature. We selected the GoogleNet, the ResNet, and the SqueezeNet. The reason of this selection is that these three type of neural network has the lowest depth and the lowest number of parameters. Okay. And the reason for that is that we wanted to avoid overfitting, because when we have too many parameters, we can get overfit the model. And also we want to reduce the training times that we have. So that is why we selected these pre-trained neural networks that have the lowest depth and also the lowest number of parameters. And in order to fine-tune these neural networks, we use a learning rate of 0.001. We use a stochastic gradient descent, and the max number of epochs that we established was 25. The mini batch size was 15, and we performed fivefold cross validation. The reason of using fivefold cross validation in this case study is that since we have a relatively small sample sizes, we decided to perform this fivefold cross validation process in order to obtain an estimate of the generalization performance of the approach. Um, and also, we decided to limit the false to 5, because if we increase the false size, we can, we will need more time to train the model or fine tuning the models based on these scalograms. Okay. So based on the parameterization that I mentioned previously, we obtained the following scalograms. In the left side is the scalogram of a vehicle vertical acceleration signal associated with on-crack pavement. And in the right side, you can see the scalogram of a vehicle vertical acceleration signal associated with crack asphalt pavement. Here you can see that there is certain differences between the distribution of the energy in this time frequency plane. Okay. We can, for example, see that in the case of cracked asphalt pavement, the energy distribution is more dispersed along the time domain, and also to some extent is constrained to between the 10 to 100 hertz. For this case, we can see that the cracked asphalt pavement has a very localized position in time, but also the frequency energy distributed to higher frequencies, to some extent. So we use these scalograms to fine-tune the pre-trained neural networks that I mentioned previously. And well, let me continue. To evaluate the performance of these models, we use the sensitivity, the specificity, the precision, and the accuracy derived from a binary confusion matrix. Also, we computing the received operating characteristic curve and also the area under this curve. The reason for using this metric is also that we wanted to know how well this model performs for different classification thresholds. So we decided to use this metric to evaluate more robustly and holistically the performance of the method. So at the end, we obtain the following results that can be appreciated in table 3. Overall, we can see that by applying this approach, The SqueezeNet gave us the best performance in terms of sensitivity and specific and F1 score. Also, the ResNet 18 gave us a very similar F1 score, but you can see that the sensitivity is quite lower. And remember that the sensitivity are the percentage of values that were of positive cases that were correctly identified. Okay, so we are very concerned in how well we are detecting these uh, transverse crackings, no, by using this acceleration data and the method that we propose. So that is why we are giving more weight to the sensitivity. Okay. Well, this is the approach of using the generalized Morse wavelets. We generate a scalegram and we train a neural network, no? In particular, a convolutional neural network based on those scalograms. And the second approach that we tested was to use the scattering transform. So the idea is, okay, we will be using the scattering transform on these vehicle vertical acceleration signals. We can get these scattering coefficients, but instead of using um, a neural network to perform the classification, we will be using the scattering coefficients of the scattering transform to fine-tune, or sorry, not to fine-tune, but to train simple linear classification techniques. Okay, we want to use a linear discriminant analysis, a super vector machine, a decision tree, and the canary neighborhood. Okay. So before I get into deep into the results of applying this method, I wanted to expand a little bit about the theory of the scattering transform. So the method or the algorithm was proposed by Stefan Manlat, and in particular, he was interested in answering the following question, no? How should signals be represented for classification? So the scattering transform proposes to use a representation of the signal that meets two properties. We want to be invariant to translations and also stable to small time wrapping deformations. The idea of achieving these two properties is that we want to reduce the within class variance. Okay, we want to reduce the variability inside inside a set of signals that belongs to a particular class. And well, why we are not using the other transforms that we discussed, for example, in the case of the Fourier transform, the magnitude of the Fourier transform is invariant to translation. It doesn't care about the time shifts of the signal over time. But the problem is that it is not stable to these small time wrapping deformations that are basically small escalations in time. And the wavelet transform is translation covariant. Since in the wavelet transform we have this time resolution, it makes it dependent to signal translations over time. So, well, the parameters that we use to compute this scattering transform, well, here in this case, the algorithm is a MATLAB implementation that already performs this scattering transform, and it uses a complex modeled wavelet, okay? And also we compute or we set there are two parameters that is called invariance scale. That is the size of well, I will explain about the parameters in a second. First, I wanted to introduce the method. Okay, so this is an overview of this technique, where I will try to explain to the best I can this algorithm. Basically, as you can see, we have the signal, and we are basically performing a wavelet transform to this signal. Here you can see the convolution between the signal and a scaling function or a Fadder wavelet. This convolution is basically extracting the low frequency information of the waveform, but in order to recover the rest of the frequency spectrum, we need to compute the convolution with a family of dilated wavelets that cover the rest of the frequency spectrum. And that is the reason of having this convolution. But contrary to the wavelet transform, we are getting the modulus. And this is a crucial step, but because since we are imposing that the wavelet is complex, um, in other words, it is analytical, we can, the result of the convolution between the signal and a complex function is a complex function, no? So when you get the modulus of a complex function, you can get the envelope. That is basically low frequency signal, okay? So we are extracting, or we are, in some sense, translating the higher frequency informations to lower frequencies by computing this modulus, and then we are filtering the results. And this first result is called the zero order scattering coefficients, and these are the first order scattering coefficients. You can see here that again, this envelope is convolved with this scaling function, and but the problem is that, well, when we are filtering again the information, we are losing some of the high frequency information that is extracted from this modulus. So in order to recover the information that we lost from the first order scattering coefficients, what we can do is to take this modulus result and apply a second convolution with a second family of dilated wavelets that cover the rest of the frequency spectrum. And well, based on this result, we compute again the modulus. We are basically extracting the envelope of this result. And again, we filter the information. And the reason of having these filtering operations, that in this case, we are using this filter again to compute the second order scattering coefficients, is that we want to create an invariant over time. Okay? So one way to produce an invariant is basically to average the waveform. And so basically, in some sense, you can understand this scattering transform as essentially translating the higher frequencies to lower frequencies with the purpose of generating an invariant of the signal that also meets this small time wrapping deformations property. Okay? And we are using these scattering coefficients, these zero first and second order scattering coefficients as features to train the classifier. Okay. So why not the Fourier transform? No, I want to expand on that. Well, the Fourier transform is basically defined in this format. You take the integral of minus infinity to infinity of this multiplication. And let's say that we have translated the x of t by an amount c. So we can say by the shifting property of the Fourier transform that the shift x of t signal is the Fourier transform of the shift signal over time, or the translated signal over time, is equal to this. You can see that you can get your original Fourier transform and you multiply it by a complex exponential, okay? But this complex exponential has a magnitude of 1. So it doesn't affect the result of the original Fourier transform. Okay, so that is useful because this basically means that the magnitude of the Fourier transform does not change due to translations. That is, the Fourier transform of the translated signal is equal to the original. However, for deformations, that is basically a scaling over time of the following form, minus epsilon, where epsilon is small. Well, we obtain the next Fourier transform. Based on the scaling property of the Fourier transform, we get the next expression. Basically, this means that we are shifting the signal in frequency when we are performing this small scaling over time. So this parameter affects or moves the frequencies of the signal, okay? That is why we say that the Fourier transform is not stable to small time wrapping deformations, because when you have a very high frequency in your original waveform, but you deform it a little bit, you can see that this term will shift the higher frequencies to even more higher frequencies because of this term. Okay, so that is why we are not interested in the Fourier transform, because if shifts the frequency, the deformation shifts the frequency components to higher frequencies, and this makes the comparison between similar signals very difficult because they are not the same anymore in the Fourier domain. And why not we are using the wavelet transform? Well, as I mentioned before, in the wavelet transform, you have this time resolution. So since we have this dependence on time, well, this representation is not a translation invariant. On the contrary, it is translation covariant. Okay, and this is also associated with this convolution, no? That we're computing between the signal and the wavelet, no? Because the wavelet transform is essentially a convolution between two waveforms. Okay, so, well, you can apply this technique to the data, no? It's just only an preamble that I make in order to explain its properties. Um, but at the end, in simple terms, we can compute these scattering coefficients and use these scattering coefficients to train the classifier that we need. And well, in this case, we use very simple classifiers. We use a linear discriminant analysis, a support vector machine, a decision tree, and the kind nearest neighbors. But in overall, we can see that the linear discriminant analysis gave us the best performance compared to the other approaches that we tested. And well, here is a comparison with the literature. For example, in the first row, you can see that the work from which we get the data set obtained an accuracy of 95.25% and an F1 score of 85.25. By using the SqueezeNet and the generalized Morse wavelets, we obtain an accuracy of 89.33. We obtain a sensitivity of 84.32 and a specificity of 92.70 and F1 score of 85. That is quite similar to the values reported by Young. And by using this linear discriminant analysis, we obtain a lower performance, no, if we compare it to the other two approaches. Okay. Here are the rock curves and also the AUC values. By performing this detection using the linear discriminant analysis, you can see that the rock curves that we obtain for each of the folds are closer to this diagonal line. Contrary for the SqueezeNet and using the generalized Morse wavelets, we can see that the rock curves are far away from this diagonal line. And also we obtain better values for the AUC compared to the AUC values of the linear discriminant analysis trained with the scattering coefficients. Despite these results, it is important to highlight that the SqueezeNet, one of its main disadvantages is that it's a training time. Okay, you need specialized hardware like a GPU to train the classifier. In the case of using the scattering transform, you can use a linear discriminant analysis to train with the scattering coefficients, and you need a CPU. In this case, I was using this model of Intel processor, and also the training time is from seconds. Okay, you can train these classifiers in 0.14 seconds by using this processor. In this case, you need more power and also more time to train the classifiers. Okay. And also there is a contrast in interpretability, no? The linear discriminant analysis is more simple compared to the SqueezeNet that requires or that has more than 1 billion parameters. Like here we have approximately like 21 parameters. So, well, the conclusions for this first case study are the following. This work compares transfer learning and the wave scattering transform for pavement traverse tracking detection based on the vehicle vertical acceleration signal. The results show that fine-tuning the SqueezeNet using the generalized Morse wavelets provided better accuracy, sensitivity, specificity, and AUC than a linear discriminant analysis trained with the wave scattering features. However, compared to the regularized linear discriminant analysis, the SqueezeNet requires a higher training time and a greater number of parameters. And well, these are some of the publications that are a result of this work and of this comparison. Also, we have some conference works. And, and now I want to go to the following case study. Well, these are the reference for this part, for this first part of the presentation. Now I want to talk about water leakage classification, okay? So first I wanted to make a motivation. Why we want to study this idea of detecting water leakages. So well, let me drink some water, just a second. Okay. So well, the motivation behind studying this idea of how can we can detect water leakages, is that, well, water distribution networks are typically affected by these water leakages. Um, and these losses represent between the 15 to 50% of the total water volume. And these water leakages can be a consequence of aging pipelines and soil subsidence. And well, also this um, presence of leakages in the water distribution networks can produce water scarcity, water contaminations, and also require maintenance costs. So, well, in the literature, there is already a great plethora of works that have tried to detect water leakages. For example, you can use hardware methods that basically rely on using thermography, acoustic emission data in order to detect these water leakages. But the problem is that they are expensive and time consuming. So another approach are to use is to use, sorry, software methods like hydraulic models of the water network or data-driven models. The problem of hydraulic models is that you need to know the parameters of the pipeline, no, in order to detect the parameters of these hydraulic models correctly, no, in order to correctly set the model that you want. And you can use also data-driven methods, but you need to require large training times and a large sample size to use this data-driven approach. Um, Also, we notice that in the literature has been focused only on detecting the presence or the absence of the water leak. Also, well, there are different data modalities that you can use to generate a data-driven model for detecting these water leakages, like vibration data of the water network, hydrophone data, or acoustic data, or also you can use pressure data or flow data. The problem is that there is no comparison between the different data modalities that you can use in order to perform this detection, no? And well, most of the literature has been focused on only using these different data modalities separately without considering at the same time. So here in table one for this new section or for this case, for this second case study, I make a summary of some of the works that are already available in the literature. As you can see, there is certain diversity between the signal that is used, but again, it's quite interesting that for this new problem, we are again seeing these frequency domain features, no? To train machine learning, gradient boosting trees, deep neural networks, and so on. And also we can see that there is a relatively high performance, no? Regardless of the method that they use, always the accuracy is relatively high, no? But the problem is that we cannot compare fairly these results because some studies use other data sets that are different from the data set that the other authors use. So telling which is one is better is difficult, no? Because there is a lot of heterogeneity between the data sets or conditions that the authors consider. So, well, for this problem, we focus more on using, we wanted to compare the use of acceleration, pressure, and acoustic data. And also we use this scattering transform of this data to train a super vector machine, a candidate's neighbor, and decision tree. We selected these three classifiers because they are one of the simple ones and they are easy to train. And also, they are frequently used in the literature. The main difference is that contrary to previous study, this scattering coefficients or this wavelet scattering transform was not being used at the time that we developed this model. And well, we train the classifiers to detect water leakages in loop and branch water networks. And based on the best performance or the best model trained for the different data modalities, we generate a late fusion model that by using a majority voting mechanism or a hard voting approach. So this is the data set that we use for the analysis. The dataset is publicly available. Basically, it consists of two water networks. One was a loop water network and another was a branch water network. The position H1 and H2 refers to the hydrophone data that they use. They are basically placed at position where hydrants were simulated. The accelerometer data, that is position A1 and A2, are are the position of the accelerometer of the accelerometer sensors that were placed in T connections of the water network, and position P1 and P2 refers to the positions of the pressure sensor. Okay. Also, M1 and M2 refers to the positions of flow sensors. Okay, but for this study, or at least the authors did not collect these, or they do not reported the data from these flow sensors. And also the leak position was placed at the middle of the water network. And well, we do the same thing for the branch water network. The position of the sensors is the same, but the configuration of the water network changes. In total, we have 1,200 signal segments of 1 second for each data modality and water network. Also, we have different types of leakages. In the literature, typically they analyze only the presence or the absence of the water leak. Here, we wanted to test this approach by detecting circumferential leak, longitudinal leak, orifice leak, gasket leak, and no leak. Also, the data set is balanced. In this case, there is no representation or representation of these water leak types. And well, here I place what is the meaning of A1 and A2, and also the sampling frequency, no, of each of the of each of the data modalities that were considered. Uh, for the vibration or the pressure data, the sampling time or the sampling frequency is essentially the same. For the acoustic data, they use a different acquisition system, but was sampled at 8 kilohertz. Okay, so the approach was as follows. We take this acceleration, pressure, and hydrophone data. We apply the wavelet scattering transform to each data modality, and we obtain scattering coefficients. Then, with these scattering coefficients, we uh, train three classifiers: the supervector machine, the decision tree, and the k-nearest neighbor, by using a 10-fold cross-validation. And also, we use this 10 cross-validation process for hyperparameter tuning. And finally, we use a different test set in order to evaluate the performance of the approach. Well, we compute all of the metrics, precision, recall, F1 score, and so on, and also the area under the receiver operating characteristic curve. So in order to illustrate better this cross-validation process, and also the split between the training and test sets, well, as I mentioned before, from the 100% of the data, that is the 1,200 signal segments, we use 80% for training the models and using tenfold cross-validation on this training set, and the final data sets that represents 20% of the data set were used for testing, no, the results. So many of the results that I am showing you here are the results of these data sets. And again, we use the accuracy, precision, recall, F1 score, the area under the rock curve, and the AUC, you know. Here, I wanted to mention that, well, here I'm showing you the scattering coefficients of acceleration data associated with the branch water network. These essentially are the coefficients that we use to train the classifier. In the right side are the same scattering coefficients, but for the case of the loop water network. But these points or these values were the ones that we use as a feature vector to train the classifiers. And well, based on these scattering coefficients, we notice that the best performance in terms of testing accuracy was the ones for related to the supervector machine. No, this was the classifier that gave us the best performance for both the loop and the branch water network. Here are the scattering coefficients associated with the pressure data for the branch water network, and these are the scattering coefficients of the pressure data for the loop water network. Again, we use these scattering coefficients to train the classifiers that I mentioned previously. Again, we noticed that the supervector machine was the best one in terms of testing accuracy. And Well, we also perform the same for the hydrophone data. These are the scattering coefficients for the branch water network, and these are the scattering coefficients of the loop water network. Again, we use these values to train the classifiers. And again, we notice that the support vector machine was the one that gets the best performance in terms of testing accuracy compared to the other classifiers for both water networks. This is a summary of the best classifiers for each of the data modalities. This is for the vibration data, the pressure data, and the hydrophone data. Here we can see that the vibration data trained with a support vector machine gave us the best performance of terms of testing accuracy. And also, well, based on the best classifiers, we trained this late fusion model. But before moving to the late fusion model, here I am showing you the rock curves and the area under the receiver operating characteristic curve of the SVM trained with acceleration data. Here you can see that the rock curves are very close to this point 1, and also they are far away from this diagonal line. And also the AUC values are greater than 0.98. This is for the loop water network at the right, and in the left is for the branch water network. Again, the results are relatively high. Again, just to be precise about this, these are the rough curves derived from the test sets. And well, finally, well, I was mentioning previously that these are the best classifiers. We use these best classifiers of each data modality to train a late fusion model by applying this majority voting mechanism. That means that we make a prediction for each of the models generated for each data modality, and then we make the final prediction by performing the majority voting mechanisms of the predictions of each of the classifiers. And well, here are the results. This is the late fusion model for the loop water network. We obtained a test accuracy of 93.33. And for the branch water network, we obtained a test accuracy of 95.83. And well, are the the rock curves. Here again, this is for the branch water network, and this is for the loop water network. You can see that the rock curves are very close to one. And but as you can see, well, there is too much difference, no? In terms of having a better performance by combining the results of each data modality. At least for the data set that we have, it seems that the acceleration data gave us the best performance compared to using the three data modalities at the same time by using this late fusion model. So just 1 second. Let me just 1 second. Okay, so let me continue this. Okay, so well, as to complement this analysis of using the scattering transform with the for water leakage classification, we wanted also to test the generalized Morse wavelets. Okay, so well, again, the idea is we will be using um, this data that we have. In particular, we will be using only the acceleration data for simplicity. We make this decision based on the fact that the acceleration data or the vibration data gave us the best performance by using the scattering transform. So we wanted to use that data to simplify the analysis. So we will be generating an scattergram derived from the generalized Morse wavelets to fine-tune these pre-trained neural networks. Okay. So the idea is as follows, no? In order to compute this scalegram, we need to define the parameters of gamma, beta, and the voices per octave. So again, we use the signal, we apply the wavelet transform, we generate wavelet coefficients, we compute the inverse wavelet transform, we obtain a reconstructed signal, and we obtain an error. Okay? And Based on this error of all of the data set, we uh, generate the scalerogram that we will be using. Well, we will set the value of beta to generate the scalerogram that we need to fine-tune these pre-trained neural networks. Again, we will be using the average reconstruction mean square error because we have many signals. If we only use the error, we will be only considering the error of one signal. So we apply this error to all of the signal segments. And based on that, we compute the surface of the average reconstruction mean square error. In the left side is the curve of the surface for the branch water network results of acceleration data. Here you can see that for the branch water network, we define, well, the minimum reconstruction error occurs when we have beta equal to 2 and 2 voices per octave. And for the acceleration data of the loop water network, this is the surface. And we notice that beta equal to 1.66 and 1 voice per octave gave us the minimum average reconstruction mean square error. Also remember that we are setting gamma equals to 3 based on the lower bound of the Heisenberg area. Okay, here I am only marking in these red squares the position of the minimum error that is also denoted by these red dots that you can see here in the two surfaces. And well, here are the results of the scalograms of acceleration data associated with the branch water network for each of the different types of water leaks that we analyze. This is the results for the loop water network. And again, we use these scalograms to fine-tune this pre-trained neural network. And well, in this case, we only use the SqueezeNet and the GoogleNet, mainly because these types of neural networks have not been used in the literature. And we noticed here that the SqueezeNet gave us the best performance for both the loop and branch water network when fine-tuned with these scalograms, no? And this is the parameter settings that we define, no, to train these neural networks. Here are the ROC curves that we obtain from each of the, well, this is in the left side is the ROC curve of the supervector machine trained with the scattering coefficients of acceleration data. And in the right side, you can see the results of the ROC curves or of the SqueezeNet trained with the scalograms generated via the generalized Morse wavelets. And well, these are the records of this approach. No, using the SqueezeNet plus scalegram generated by the generalized Morse wavelets. Again, you can see that in terms of the rock curves, but also the AUC, we are getting a better performance by using this scattering transform compared to using the SqueezeNet plus the scalegram generated with these generalized Morse wavelets. Well, this is the results for the branch water network, and these are the results for the loop water network. In the left side are the results of the SqueezeNet, and on the right side are the results of using the scattering transform to train the supervector machine. And well, here you can see that we are getting a relatively high performance in terms of AUC. Okay, and well, this is the training time. Again, for the SqueezeNet is relatively high. Also, it's higher because we have a higher data set. Here we need to train the model by 14 minutes and 4 seconds, but using this supervector machine, you can train this in 11 cycles, no? So the computational, at least for this data set, the scattering transform gave us better performance in terms of performance, well, an actual performance or the metrics that I showed previously, but also in training time, no? It has its advantages. So the conclusions of this second case study is that, well, the scattering coefficients of accelerometer data combined with a supervector machine achieve the highest performance, highest classification accuracy for water leakages, reaching 89.6% for the loop water network and 96.7% for the branch water network. In contrast, the late fusion model yielded a higher accuracy of 93 for the loop water network, but performs worse than the supervector machine with accelerometer data for the branch water network. Compare by comparing this scattering transform and the squeeze-net, we can say that the waveless scattering transform of acceleration data performs better in classifying water lakes than the squeeze-net. Furthermore, the scattering transform training time is lower than fine-tuning pre-trained networks, no, like the squeeze-net. These are some of the publications that are a result of this second case study. We have one journal article, one conference paper, and one co-author publication that it's related to this topic, of water leakage detections. And also we have a paper under review in a journal, in which we are studying what are the effects of varying the parameters of the scattering transform. But I don't listed that publication right here because, well, it has not been published, it's under revision. And these are the references that I use for this study. And, well, currently as future work, one of the doctoral student, one of our PhD partners is working in how the parameters of the scattering transforms, how affects the classification of water leakages. And also we are comparing the use of the scattering transform with manual features. No, that is a work that has not been explored until this point. And, well, that's it for me. I hope you like this presentation and see you later.